This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about a recent solids test, CE 3303. We've got a combined loading problem here with a sign cantilevered off of a post, and it's a 2-inch diameter post. The weight of the sign is 600 pounds, and we'll make this really easy on you. We just give you the internal reactions. Really, we start off with kind of a statics problem. It's a 3D statics problem, and the sign has wind blowing on it, which is 20 psf. The sign's area is 3 by 1, so that makes 3 times 1 times 20, or 60 pounds. That is a horizontal force like that. Anyway, those two forces, the weight of the sign and the wind load, produce 5 of the 6 possible reactions. Now, we're looking at a point down here. We're making a cut 3 feet below the sign, and we're saying that here's the internal reactions. Now, these are in statics, we would call that, whatever that point is called, AX, AY, and AZ. And then we have the moments about those axes, MX, M at A, MY at A, and then we would call this in statics MZ at A. So they translate in solids to these forces. The AX is translate to VX, which is 60 pounds, which is that wind force, which is an X direction force. It's a shear. AY is 0. There's no force in the Y direction, so VY is 0. AZ is the weight of the sign. It's a Z direction force, negative 600 pounds. So we see that the column or the post is in compression due to that. Then we have these 3 bending moments, 2 of which we think of as bending moments, 1 of which is torsion. MX is the moment about the x-axis, which is this axis right here, and it is caused by the weight of the sign, 600 pounds times 1.5 feet away. We have a moment about the y-axis, which is this axis here, through the cross-section. And that's caused by the wind load, 60 pounds times 3 feet. And then we have a torsion caused by the 60 pounds, the wind load, and it's 1.5 feet away from the z-axis, so that's 60 pounds times 1.5. So that's how we got those. We say in the instructions, magnitude is shown of these reactions, and you must determine the direction of the reactions, because that's critical. We want to know tension or compression, or what's the direction of the shear force or shear stress. So primarily, we didn't even ask you for really, or care about the direction of the shear stress, because of the way the problem worked out. But we need to think about, for these normal, or for these straight line forces, and then for the bending moments, what direction we have of stress, compression, or tension. Okay, so let's look at the problem. Number 11 was, given these internal forces, determine the normal stress at point D. So we want to know the stress at this point D over here on the right side lies on the y-axis. Okay, so first clue is normal stress. Well, there's 3 ways, or 2 ways really, of getting normal stress. Normal stress is sigma, and it's either P over A, axial stress, or bending stress, MY over I stress. And you have 2 axes of bending. So you could get normal stress from either one of those moments, or both. So, let's look at this. Let's do the easy one first. Sigma due to P over A is sigma axial. And the normal force is the 600 pounds. So that's the force. It's negative because it's in compression. If you look at the reaction on that section, it would be up to resist the downward weight of the sign. So it's negative for compression. 600 pounds is the force, and the area of that post is just pi over 4 times 1 squared, or 2 squared, the diameter of the post, and this works out to be negative 191 psi. Now we have bending, and we have bending about both axes, but if I look at point D, it lies on the y-axis. Therefore, the bending due to the y moment is 0. So I get sigma y is equal to 0 because it lies on the neutral axis. It does not lie on the neutral axis for mx, and I need to look at the direction of mx. mx is 900 pound-feet. It's caused by the weight of the sign, and therefore it's trying to create, it's like a moment like this on the top of that section. It's trying to create, it does create compression at point D, tension on the opposite side. So the moment's that way, so I'm going to have negative sigma x on this side, positive sigma x on this side of the x-axis, tension. But D is on the negative side, so I just need to figure the numbers. So sigma x is just equal to the moment, 900 pound-feet. I need to get it into pound inches, so I multiply by 12. So you know this formula is my over I. The y distance is the distance from the neutral axis, so that's just, it's a 2-inch diameter circle, so that's just 1 inch. And then I need the moment of inertia about the x-axis of a circle. And that is just pi over 4 r to the 4th. The radius is 1. 4th power. And this is compression, so it's a negative stress. So I run the numbers and I get negative 13,750. I've got pound, feet. This converts it to inches, the 12. And I've got inches on the top, and I got inches to the 4th on the bottom. I check my units and I end up with PSI, pounds per square inch. And I need to combine those with superposition. So I say 191 plus 0 plus 13,750, all negatives, ends up with negative 13,940 psi. That's the answer. Okay, now I have part 12, number 12, given the internal forces, determine the shear stress at point C. Okay, there's 2 or sort of 3 ways I can get shear stress. Shear stress is tau, and it's either transverse shear stress, VQ over IT, or it's torsion shear stress, T rho over J. So, let's look at it one part at a time. Okay, I do have a straight line shear of 60 pounds in the X direction. I have 0 in the Y direction, straight line shear, and I have this torsion of 90 pound-feet. So let's look at the straight line shear first. Okay, so the shear, if I draw this section bigger, there's the x-axis, there's the y-axis, there's point C that I'm concerned with. Okay, so the shear is in the x direction. It's coming from the wind force. So that's Vx on the section, 60 pounds. Okay, there is no shear stress at the extreme fiber because Q is equal to 0 up here. y bar prime A prime. So because of that, the shear stress due to Vx is equal to 0. So I would say tau due to x direction shear is 0 because C is at the extreme fiber, at the furthest point from the neutral axis. If I've got Vx shear in the x direction, the axis that I'm dealing with, if I had any, would be the y-axis. It's perpendicular to this y-axis here. But C is at the extreme fiber, the furthest possible distance from that. So Q is 0, as I said, and tau x is 0. Then I have no shear force in the y direction. If I did, I would have to figure VQ over IT, but Vy equals 0. Therefore, I say that tau in the y direction due to y shear is 0. So the only thing I'm going to have is torsion shear. Tau is equal to T rho over J. Okay, so the torsion is this 90 pound-feet. Once again, I want to convert it to pound-inches, multiplying by 12. Then rho is the distance from the center. It's the radial distance. So for point C, it's just that 1-inch radius. J for a solid post is pi over 2 r to the 4th, or c to the 4th, c outside as it's shown on the equation sheet. So this works out to be 687.5 psi. That's the answer.